Hello everyone. So from now onwards, I'm going to make some videos on maths background for thermodynamics, and in these videos, we'll be discussing the concept of what do we call partial differentiation. So here, partial differentiation, and what are the topics we are going to discuss in this partial differentiation. So the first point, so what is the meaning of partial derivative? What is the exact meaning of partial derivative? What is the difference between normal derivative and partial derivative? And the second point, what are the rules we follow while doing partial differentiation? While getting the first derivative, partial derivative, what are the rules we are going to follow? That is the second point we are going to discuss. And the most importantly, how to get the second derivative. In partial differentiation, how to get the second derivative. That is the point we are going to discuss. And the next one is some important rules like cross derivative rule. Cross derivative rule, that is Euler's reciprocity relation. Euler's reciprocity relation, that is the rule we are going to talk about. And the next one is relation between partial derivatives. Relation between partial derivatives. And also the next one, that is chain rule. And finally, that is cyclic rule. So these are the things we are going to discuss under maths background for thermodynamics, for the concepts of thermodynamics, particularly essential criteria for state function. Essential criteria for state function. To understand that essential criteria for state function, we need what do we call some basics like partial differentiation. And without making any delay, let us start the actual concept. So that is partial differentiation, that is partial derivatives. Partial derivatives. So what is the exact meaning of a partial derivative? So first let us understand the definition of this and what is the meaning of this, we'll try to understand. So the derivative of a function, the derivative of a function with respect to one of the independent variables. Basically, it is a derivative of a function with respect to one of the independent variables, but while getting this derivative, all other independent variables are kept constant. So what does it mean? What does it mean and how to understand this? For example, let us take a z is a function of what do we call x and y. Let us take z is a function of x and y. So very clear in this z depends on x and y. And while getting this partial derivative, what we have to do is either x should be kept constant or y should be kept constant. For example, I'm keeping y constant and I'm going to get the first derivative of z with respect to x. First derivative of z with respect to x we are going to get. And x is kept constant. X is kept constant and we are going to get the first derivative of z with respect to y. So for this partial differentiation, we use the symbol. What do we call? We read it as a del. We read it as a del generally. So here that is a dou z by dou x, dou z by dou x. So this is a derivative of z with respect to x, but y is kept constant. Y is kept constant. And similarly, you can get the derivative of z with respect to y, but x is kept constant. X is kept constant, and here z is a function of x and y, and x and y are independent variables. And while getting these partial derivatives, so what we are doing is except x, remaining what we call all other independent variables are kept constant. If you get the derivative in this manner, the result is called what we call partial derivatives. This is the definition of partial derivative. So the derivative of a function, with respect to one of the independent variables. So this is the derivative of function with respect to x, but here y is kept constant. If you get the first derivative in this manner, the result is called what we call partial derivative. And the process is partial differentiation. And most importantly, these derivatives arise when a function having two or more independent variables. For example, here z is a function of x and y. So here it is having two independent variables. So the partial differentiation comes into the picture when a function has two or more independent variables. For example, it may be like z is a function of KLM. In that situation also we can get what we call a partial derivative. So for example, remaining two independent variables should be kept constant, and you have to get what we call a derivative with respect to a particular independent variable. So these derivatives arise when a function having two or more independent variables is differentiated. And what are the rules we follow while taking these partial differentiation? What are the rules we follow? Exactly, partial derivatives are evaluated by the rules for ordinary differentiation. While doing ordinary differentiation, whatever the rules we follow, even in partial differentiation, we follow the same rules. So this is exactly the definition of partial derivative. And when do we do partial differentiation? What are the rules we follow while doing partial differentiation? And let us understand this by taking one example. Here, I'm talking about ideal gas. Volume of 1 mole of ideal gas. Since it is 1 mole of ideal gas, I can say molar volume. So molar volume of ideal gas is a function of temperature and pressure. You know ideal gas equation, and the ideal gas equation, volume of ideal gas is equal to nRT by P. Since I'm taking 1 mole, obviously that is molar volume is equal to RT by P, and R is universal gas constant. And this molar volume of gas depends on temperature. It also depends on pressure. So molar volume of ideal gas is a function of temperature and pressure, right? And now I'm going to get the partial derivative of molar volume of ideal gas. See, for example, here there are two independent variables, but while getting the partial differentiation or partial derivative, what we are doing, I'm going to get a partial derivative of molar volume with respect to pressure at a constant temperature. Temperature is kept constant. We are keeping temperature constant, and by keeping temperature constant, if you change the pressure, how molar volume of ideal gas will change? If you change the pressure, how the molar volume of ideal gas will change? So here, with respect to pressure. So this is derivative with respect to pressure. Derivative of molar volume with respect to pressure at constant temperature. And this is the representation already told you. Partial derivative, the symbol is like this we use, and this is read as del. So del V by del P at constant temperature is equal to. So here molar volume of ideal gas is RT by P. I'm just putting RT by P here, and we are doing at a constant temperature. Already told you the mode of partial differentiation, whatever the rules we follow in a normal differentiation, here also 100% we follow the same rules. 100% we follow the same rules. And here R is a constant. Temperature, of course, in this process, temperature is kept constant. And what is the variable here? Pressure. You know, pressure is in the denominator. If it comes into the numerator, so what happened? That becomes a P power minus 1. P power minus 1. In the normal differentiation, you know, so the power will be coming as coefficient, and here we have to do -1. So that becomes a minus RT, my RT, R is constant, T is constant, minus RT P power -2, that P power -2 in the denominator, that becomes a P square. So the procedure is same. Whatever the rules you are following in normal differentiation, here also you are following the same rules you are following. But the thing is, actually molar volume of ideal gas is a function of temperature and pressure. But while getting this particular derivative, so this is derivative of molar volume of ideal gas with respect to pressure by keeping temperature constant. What is the result? Minus RT by P square. For example, there is one more function, that is pressure. So here, and one more, that is what do we call, one more independent variable, that is temperature. Now let us find the derivative of molar volume with respect to temperature at a constant pressure. We are going to get the derivative of molar volume of ideal gas with respect to temperature at a constant pressure. So whatever it may be, molar volume of ideal gas is RT by P. And in this process, very clear, pressure is kept constant, R is constant. So here differentiation of T with respect to T is 1. So the result will be R by P. So this is del V by del P at constant temperature, del V by del P at constant temperature, and this is del V by del T at constant pressure, and this is molar volume of ideal gas, and this is the definition of partial differentiation, and this is the procedure we follow while doing partial differentiation. While getting partial derivatives, these are the rules we follow. And the next one, second derivatives. Frequently we do this second derivatives. So you are going to get the second derivative. See, let us understand this. For example, z is a function of x and y. Z is a function of x and y, and the first derivative just now we discussed. So here this is del z by del x at constant y, and another first derivative is del z by del y at constant x. So this is first derivative of z with respect to x at constant y. This is first derivative of z with respect to y at constant x. What we are going to do here, we are going to get the second derivative. Second derivative means whatever the result you are getting for first derivative, again it is subjected to differentiation. Again it is subjected to differentiation. For example, second derivative, again if it is subjected to differentiation, so this is the first derivative. So del z by del x at a constant y, this is whatever the result you are getting, again this is subjected to differentiation with respect to x by keeping y constant, and whatever the result you are getting, that result is called second derivative. So second derivative, so this is del square z by del x square, del square z by del x square. If I take one example, it will be more clear to you. So here this is the first derivative, again this is subjected to differentiation with respect to x at a constant y. So ultimately it becomes del square z by del x square at a constant y. Similarly, this is the first derivative. Again, if the first derivative is subjected to differentiation, del z by del y at constant x, again it is subjected to differentiation. As a result, you will be getting what we call del square z by del y square at a constant x. And you can do in this combination also. You can do in this combination del square z by del y del x, del square z by, this is also second derivative, no doubt. But what exactly we are doing here, the first derivative is del z by del x at constant y, del z by del x at constant y. Whatever the result you are getting, that result is subjected to differentiation with respect to y, but while getting this second derivative, x is kept constant. So in any fashion you can do, in any manner you can do. Same thing, this is a del square z by del x del y. So what does it mean? So this is the first derivative. So here if you see these two here, this is first derivative of z with respect to x at a constant y. This is the first derivative of z with respect to y at a constant x. the result what you are getting is again differentiated, and that is with respect to 2x at constant y. So whatever the result you are getting in the first derivative, that result can be differentiated again, and if you get the derivative in that manner, that is called a second derivative. And in this, let us take one example, it will be clear to you under second derivatives. If I take one example, it will be clear to you. So this is molar volume of ideal gas. So this is the first derivative of molar volume of ideal gas with respect to pressure at a constant temperature. And just now we derived molar volume of ideal gas. Molar volume of ideal gas is RT by P. And this is differentiated with the P at a constant temperature. This is the result, right? Similarly, molar volume of ideal gas. This is the first derivative of molar volume of ideal gas with respect to temperature. So here molar volume of ideal gas is RT by P, but here pressure is constant, R is constant, and here T, what do we call a differential of T with respect to T is 1, and the result is like this. And this is the first derivative, and this is the result. And whatever the result you are getting, again it is subjected to differentiation. Again it is subjected to differentiation. If you see second derivative, if you see the second derivative, so this is first derivative, molar volume of ideal gas is differentiated with respect to pressure at constant temperature, and this is again differentiated with respect to pressure at constant temperature. The first derivative is again differentiated with respect to what we call pressure at constant temperature. So what is the result here? This result I am substituting here. That result I am substituting. What is the result? That is a minus RT by P square. And of course, temperature is kept constant. T is constant, R is constant. The same logic, P square in the numerator, it becomes P power minus 2. Now the power is minus 2. In differentiation, power is converted to coefficient. So minus into minus 2, minus into minus 2, that becomes plus. And that power is, what do we call a P power minus 2 minus 1. P power minus 2 minus 1 means that becomes minus 3. So the result will be RT P power minus 3. That P power minus 3, if you bring this into the denominator, so that the power is minus 2, that power minus 2 is becoming coefficient. The result is like this, 2RT by PQ. So this is the second derivative of molar volume of ideal gas with respect to pressure at a constant temperature. How to report your answer? Otherwise, let me take another first derivative we have. This is the first derivative. Again, it is subjected to differentiation. Again it is subjected to differentiation. So this is molar volume of ideal gas. So this is the first derivative of molar volume of ideal gas with respect to temperature, and the result is R by P. The result is R by P. Again, if it is subjected to differentiation with respect to temperature at constant pressure. So what is the result of this? R by P. But here P is a constant, R is a constant. So R is constant, P is constant. So obviously derivative of a constant is 0, and the second derivative will be 0. Second derivative will be 0, and this is the brief introduction to what do we call partial differentiation. So what is the difference between partial differentiation and normal differentiation? What are the rules we follow, and what is the meaning of second derivative, and how to get the second derivative? And I told you, so I'll be making some short videos on the concepts of maths background for thermodynamics, and in the next video we'll be discussing the various rules. So actually the basic thing is to understand essential criteria for what do we call a state function. We need some basics, and those basics we are going to discuss, and the next cross derivative rule, that will be discussed in the next video. So thank you very much.